Awesome. So we'll go ahead and get started. So they pushed an update to WebR to where now you can, put it into slides. So I'm going to attempt to use it today, and hopefully you guys will also use it, and hopefully it'll work flawlessly, and we can continue to use it. But if there's any hiccups or there's anything that goes wrong with it, let me know because I will not use it anymore. But we're going to attempt, hi Brooke, we're going to attempt to use it today. So when you go to actually click on the slides, what my suggestion would be to actually open this up as a PDF instead of an HTML. So what you would do is you'd press the E button, and that's going to open this up into a PDF. And what you can do is you can still run through the code chunks as a PDF, but you can actually save the code that you type and also the code that I type, right? So if you follow along with the lectures, you can type in the code, you can modify the code, and then you can save it as a PDF, right? And put it in your files. I don't know how you guys are taking notes, but this is probably what I would suggest to do. If you just follow along with the HTML slides, you won't be able to save any of the code. Then I'm in contact with the developer to see if anything can be done. But I don't think there can not something that can be done very soon or very quickly. So I think that this is the next best solution.
How do we find the link to the
Yeah. So you can also do that. Sorry. So you could go to the website, and then there's a little view the source at GitHub, and then navigate to the slides. So for this particular section, what you would want to click on is this R. So the 13 interactions R, that will give you the R code, the R chunks. So you have to use different chunks for WebR. So if you're going to follow along in actual RStudio, you just have to click on this particular QWERTY document. So then you can just kind of click through everything. So let me know if you have any questions about that. Awesome. So hopefully this works for everyone. So did everyone get to this screen, and is it like loading packages at least? Awesome. That's a good sign. So it shouldn't take too long. So once we get to the part where we actually run some code, it should work fine. So these are the packages that we're going to be using today. These already are preloaded when we're loading the WebR stuff, so you don't have to load anything. So what we're going to be doing for today, and then also for next week, I can't believe that next week is going to be our last kind of official class, how time flies, but we're going to be focusing on interactions. And today what I wanted to do was talk about categorical by continuous interactions, and then also continuous by continuous interactions. And then next week, we're going to talk about categorical by categorical interactions. So what is an interaction? And to highlight this, I wanted to use kind of a cartoony example, but I think that it'll get the point across. So let's say that we're interested in something like plant growth, right? And what we're going to do is we're going to fit a multiple regression model. This should all look familiar to you, right? So we're going to do this in R, let's say, and use the LM function. And we're going to look at two predictors. We're going to look at sunshine, so sun exposure, and water, or amount of water that a plant receives. So within a multiple regression, the coefficients that are produced are partial coefficients, right? So it's the unique relationship between the IV and the DV. So for example, the relationship between sunshine and plant growth, controlling for water, right? So holding water constant. Alternatively, we could look at the relationship between water and plant growth. And when we look at this relationship, we're holding constant sunshine, right? So a critical assumption of a multiple regression model is additivity. So does anyone remember what additivity is? Or the assumption of additivity within a multiple regression analysis?
Is it that each predictor adds something, or like that them together is more than just them separately?
Kind of. Do you want to expand on that? So what do you mean by that? you're like, no. Anyone? So additivity is the assumption that when we're looking at the relationship between two variables, so for instance, if we're looking at the relationship between sunshine and growth, it's constant over that other variable. So it's equal across all the levels of that other variable, right? So it doesn't change, right? So that's the assumption of additivity. So if we look at the relationship between sunshine and plant growth, what we're saying, if they're additive, is that it doesn't matter the amount of water, it doesn't change that relationship between sunshine and plant growth. That's what additivity is, right? So that's a major assumption. But in this context, when we're talking about sunshine and plant growth, is that assumption valid? So who here knows a lot about plants? I'm going to look at Brooke because she's growing plants here. So is the assumption of additivity here, is that valid?
Yeah. Or wait.
So if we think of like plant growth,
Yeah.
can sunshine and water be independent of one another in terms of plant growth?
I think so. Yeah.
So stated another way, can a plant grow with just one of these things?
Oh, no.
No, right? So there's actually joint effects or there's interactive effects, right? So we actually need both sunshine and water for plants to grow. So you can't have lots of sun but no water, then your plant's not going to grow, and vice versa, right? So what we would say is that there's interactive or joint effects of sunshine and water, right? Both of these together facilitate plant growth. So what does it mean to have joint effects or interaction effects, right? So if we look at the relationship between sunshine and plant growth, what we're saying is that this relationship depends on this third variable, which is water, right? Or alternatively, we can say that the relationship between water and plant growth depends on the amount of sunshine. That's kind of an interaction effect in a nutshell, right? So a variable that alters the strength or modulates the strength between X and Y, so in our case, sunshine and growth, is called a moderator variable. So sometimes in the literature, you'll hear about moderation analysis, and I'll also refer to moderation analysis as a kind of a test of the interaction, right? In our case, we can say that the moderator variable, which we're going to label as Z, is water. But I want to make it clear that these are kind of symmetric, right? We can have sunshine as our moderator variable. It doesn't really matter, right? But here we're going to pick a moderator variable. We're going to pick water, but it could be sunshine as well. But just for kind of demonstration purposes, we're just going to choose water as our moderator variable. So there'd be an interaction within this model. If let's say we have two levels of water, let's say 0 is no water and 1 is a lot of water. So we would have an interaction effect where, let's say that there's no water, right? What we'd probably see is a very weak relationship or no relationship between sunshine and plant growth, right? So there probably wouldn't be any plant growth or maybe very minimal. The plant would probably die. However, when we have lots of water, so Z equals 1, what we see is that this relationship between X and Y, between sunshine and growth, becomes a lot stronger, right? And we'll have luscious plants. So if we go into Brooke's office, just bustling plants everywhere, right? If we have lots of water. So this interaction effect, how do we incorporate it into our model? And it's very easy. What we're going to do is just look at the multiplicative effect of X and Z, so of water and sunshine. And all we're going to do is we're going to take our model and we're just going to multiply sunshine and water together. And that's going to be our interaction between those two. And if we're going to fit this in R, we would use a syntax that looks similar to this, where we're just going to use this little asterisk here. And that would indicate that we're interested in the interaction between these two effects. If we were just interested in the additive effects, right, we would just use this plus sign. But we're interested in this interaction. So using this syntax, we would get our separate effects of sunshine and water, but also the interaction between those two. So the multiplication of those two factors. So you might ask, what does an interaction look like in your data? Well, we have to imagine two lines, so two slopes. And if there is no interaction in our model, what we would have are parallel slopes, or slopes that look like this top row here, right? So the slopes are constant across the level of the other variable, right? So the slope is equal between the two, right? What about if we have an interaction? Well, the slopes would be non-parallel. And that's highlighted in the bottom row here, right? So we can see that the slopes are different between those two lines here. And that would be indicative of an interaction. And while the interactions could look a little different, there's kind of two general shapes that an interaction takes. One shape is a disordinal shape. So in the literature, you might have heard a crossover interaction. That's the case where we have a group or a variable that starts off high and then kind of goes low. And then for the other group or other variable, it starts off low and then it goes high, right? So these lines kind of cross over with one another. This is called a crossover interaction. There's also ordinal shapes where we might have a slope that's consistently higher than the other group. That's depicted here. Then you might have something like what's called a knockout interaction, where for one of the slopes, the slope is at 0 and the other slope is positive, or it could be negative. And this is called the knockout interaction. So these are the two general interaction shapes that you can see. Again, you're not going to get something that looks perfectly like this. Again, this kind of highlights that, right? So, but as long as there's some non-parallelity, that means that there's an interaction occurring in your data set.
What are the lines? They're using a group.
So let's say we have male versus female, right? So group 1 would be females, group 2 would be males.
Okay, and that's like a predictor?
Yeah, that would be a predictor, yep. If we're dealing with something continuous, right? It could also be something like a variable that's continuous in nature. But I'll highlight that with an example so you can see. So let's go ahead and start off with categorical by continuous interactions. So for this, I want to use a data set that we used a couple weeks ago, where we were looking at student evaluations from 94 professors from the University of Texas at Austin. And there was a whole bunch of different factors, variables that were measured. So there was a reason why I didn't want you to use categorical variables because I wanted to use them at this very moment. So that's what we're going to do today. So let's go ahead and load in our data set. So what we could do is just run our code here. And hopefully this will run in the console. Please let me know if it doesn't. So we have our data set here, right? So we have ID, we have our score. So this is the evaluation. We have age, and then we have gender. So those are the variables that we're going to look at today. And we're going to try to answer the question, does age and sex of the instructor influence instructor ratings? So the DV is going to be evaluations. And then the IV we're going to look at is age, which is continuous. We're going to look at gender, which is categorical. And then we're going to look at the interaction between age and gender. And as a note here, so in the literature, you might see Ankova talked about analysis of covariance. I don't know if you guys have seen that in the literature. This is basically an Ankova that we're doing here. But again, we're doing it within a regression framework, and I think it's a lot easier. We don't have to use a special Ankova function, and we don't have to use a whole bunch of other assumptions. We could just continue using the regression framework that we've been using here. But this is synonymous with an Ankova. So was everyone able to load this data set and get it to load? Yay, good. So as a first step, let's go ahead and look at the scatter plot. Let me see, let me make sure that everything is recording. Awesome. So let's go ahead and look at the scatter plot for our data. So this is the scatter plot that's produced, right? So we have age on the x-axis, and then we have teaching score evaluations on the y-axis, and then we have two slopes for gender. One for females and one for males here. So given our question, what do you think? What do you think the answer is to our question before we do any statistical analysis?
The question being like whether.
So yeah, so does sex and age interact here? Yeah, I would say that there looks like to be an interaction. What do you think that the nature of the interaction is, looking at this?
everyone.
I mean, in a nutshell, yeah, no, it's not very positive. But what looks like what's going on here is that as you age, evaluations go down, but more so for females. So that's what looks like what's going on here, but we can test for this statistically, right? So we can't just look at a scatter plot and be like, that's what's happening. There's an interaction here. We have to test for it statistically. So how do we test for moderation in our analysis? Well, essentially what we're going to be doing is we're just going to be adding an interaction term. And as I said before, the interaction term is just taking X times Z, or in our case, it would be taking age times gender in our data set. And essentially what we're interested in are two equations because we're interested in two slopes. So we're interested in the slope for females. So this is the relationship between age and evaluation score. And then we're interested in the slope for males. So the relationship between age and gender for males. And we can work this out algebraically, which I've done here, right? So we're going to dummy code our female or our gender variable, where Z equals 0 is for females, and then Z equals 1 is for males. And we can see here for females, the equation essentially is B sub 0 plus B sub 1 times X. And for males, the equation is B sub 0 plus B sub 2 plus B sub 1 plus B sub 3 times X, right? So we can insert our dummy coded variables into this equation, and we can extract the slopes for our analysis. So essentially it breaks down to when Z is 0, so when Z is female, the effect of X and Y is basically B sub 1 in our regression output. And when we want to see what the slope is for males, we basically take B sub 1 plus B sub 3, and that will give us our slope for males. And to test for the interaction, what we're interested in is the difference between these two slopes. So that's what the interaction is testing, is the difference between these two slopes. Are they significantly different from 0? So that's what we're going to be testing. So what I have here are 4 steps to a moderation analysis. So in step 1, what we're going to do is compute the interaction between gender and age. Again, it's just taking the multiplication between the two. In step 2, we're going to fit a multiple regression model with X, Z, and the X times Z interaction. So age, gender, and then the age by gender interaction. And then we're going to test the coefficients, whether they're significant or not, like we've been doing. Then if our moderation effect or interaction coefficient is significant, then we're going to follow that up to determine where the interaction is coming from. And then what we're going to do is we're going to display the moderation effect graphically. So these are the steps that we're going to take to perform a moderation analysis. So what I wanted to highlight here is how to actually do the interaction term, or how to compute the interaction term. So when we actually fit the model, there's a little shortcut that I can show you. So you don't actually have to compute the actual interaction and put it into your data set. The program will do it automatically for you. But I just wanted to highlight how you can do that and put it into your data set. So here, what we're doing here is we're using a mutate function, and we're adding 2 columns. We're going to do a gender treatment column. So the gender variable is just female, male. We're going to dummy code that. So we're going to turn female into 0 and then males into 1. Then what I have here is this inter object, and that's basically the interaction term. So we're taking age and just multiplying it by gender. So we can see that looks like here. Again, just to show you that it's basically just multiplying those 2 columns together, right? So 0 times 36, 0, 1 times 59 is 59, and so forth and so on. So we have one continuous variable in our data set, which is age. So what we're doing when we interact these 2 terms is artificially creating multicollinearity. So to help solve that issue, what we're going to do is we're going to center the data, which we did before the break, right? So that's what this particular code is showing, is just centering the age variable. So let's go ahead and make sure that we've centered this properly. So again, we see that we have our inter column, we have our gender treatment column, and then we have our age underscore C, which is our centered age column here. So it looks like it did its job. So that's good. All right, so now what we're going to do is we're going to fit our regression model, and we're going to put all of our predictor variables in there. And then we're going to test whether the regression coefficients are significant or not, with a special focus on the interaction coefficient. So we can run this model. This is our summary output that we should all be familiar with. But before we go and interpret the regression model, I kind of wanted to go over just kind of a general interpretation of the coefficients. So this would apply to any type of continuous bicategorical regression model that you do. So I just wanted to go over each of the coefficients, kind of generally what they mean. And then we'll use this information to assess the coefficients with our actual data here. So here we're fitting a continuous, so this is our x variable by z, which is our categorical variable regression model with an interaction, right? So b sub 0 here is going to be our intercept, right? Or the predicted or expected outcome when x, which is our continuous predictor, is at its mean if we mean centered it, and when z equals 0, so when z is female. b1 is going to be the slope of x. So for a 1 unit change in x, that's the predicted change in y at z equals 0. So at the reference level of your categorical predictor. B sub 2 is going to be the offset or difference in the intercept for a 1 unit change in z. So going from female to male. So it's the predicted change in y at x equals 0, or at its mean, if we mean centered it. B sub 3 is the critical coefficient. That's our interaction coefficient. And this is the interaction between x and z. And this is the offset or difference in the slope for z for a 1 unit increase in x, or vice versa. So let's go ahead and run our regression model, and let's go through each of the coefficients and interpret those. So let's go ahead and first interpret our intercept model. So does anybody want to take a stab at what the 4.03 represents? Correct, yep. So it's the expected outcome of y when z is female and age is at its mean, right? So this is essentially the mean for females, right, on evaluations. On evals. And we can test this by using m-means to look at the means for the gender condition. So let's go ahead and do that. So we can use our m-means function here, and we can look at the gender treatment variable. This works. So the m-means function will give us our means for each of the conditions. So we have females and males, and we see here that the mean for females is 4.04. And that's exactly what we get here for the intercept. So this is the interpretation when we've dummy coded our categorical predictor. So let's go ahead and interpret our b sub 1 coefficient, which is age. So how do we interpret this b sub 1 coefficient? So first, what does this b sub 1 coefficient represent? Yeah, exactly. So basically it's the slope of age for the female group, right? So when z equals 0. So we can say for a 1 unit increase, in age, there is a negative 0.02 decrease and evals for females. So that's how we would interpret this particular coefficient. What about B sub 2 here? So we have this estimate of 0.21. Someone that's not Kennedy or Abby. So go look back at the interpretations, the general interpretations of the B2 coefficient. I'll give you a hint. You can look at the means of the gender conditions, and that should give you a hint of what the estimate represents. Anyone? Anyone?
Is it like the effective gender on the three?
So this is just looking at the intercept difference. So if we remember, when we talked about just categorical predictor variables, right? So this would represent the difference in the intercepts. So this 0.21 is the different.
It's like the 0.25, or yeah, the 0.21, sorry. So it's like,
Yep.
yeah, the difference between
Yep.
the male
Yep.
and female professor.
Exactly. Yep. So that's just the offset or difference in our gender variable. That's what this represents. So it's the offset or difference in gender, right? So the difference between males and females on evaluations. And evals. And we can use this information to extract the actual mean of males. So what we can do is we could take this 4.03 and add it to the 0.21, and we get 4.24. But we want to work smarter, not harder. We could just use M means and extract those means. But it's important to know what these coefficients represent, and it represents the difference in the intercept values, or the means between the two conditions. So what about B sub 3? So this is our interaction term. Does anybody want to take a stab? Well, what the 0.013 represents? So this is not the intercept difference, but it's the slope difference in gender. So it's the difference between the slopes. So the difference between the slopes between males and females. I could spell. And females. For a 1 unit increase in age. So again, this is our interaction term, right? So as we go from females to males, right, a 1 unit increase in gender, right? There's a change in the slope between age and evaluations. And that change is 0.0135. All right, as we go from females to males, right? There is a 0.013 change in evaluation scores. So if the p-value is less than 0.05 here, we would say that there's an interaction.
But like, what if the estimate's like, if the estimate's 0, then you'd say there's no.
So if the estimate was 0, there probably wouldn't be a statistically significant effect. but I would just use the p-value. So Ben, all these are using t statistics, right? The t-test or the t-distribution. So yeah, so this estimate might be like 0.0. I mean, it's probably rare that you'd get something like a 0 estimate and it be statistically significant. But it's possible if you have lots and lots and lots of data, like a 0.0001 difference might be statistically significant, but probably not. But what you'd want to look at is this p-value here in this test statistic. And here, it looks like we have a statistically significant interaction, which is good because that's what our what we inferred from the scatter plot. So this is a free country and you can do what you want. So you might want to just use dummy coding, right? It might be easier for you to interpret. I like to use deviation coding, right? So 0.5, negative 0.5. So what I wanted to do is just rerun this model with deviation coding and then go through the interpretations because it's slightly different, a slightly different interpretation. So I wanted to make sure that you have that interpretation as well. If you want to do deviation coding, or I might ask you to do deviation coding maybe on Wednesday, who knows? But I wanted to go over the interpretations for deviation coding. So let's go ahead and just add in our deviation coding into our model. I think, yes, this is the right one. So what I'm going to do is just use a mutate function, and I'm just going to add in a gender sum or a gender dev code, and then run a regression model on that. So I'm going to say that female is 0.5, and then we're going to label males as negative 0.5. And then let's go ahead and run a regression on this. Let's see if I could do this. See if this runs. Did I do something weird? Why? What is wrong? Let's see if this will run. Success. Thank you. I was like, what the? Okay. Let's see. Let's see if this will run. Will not let me run it through there. There we go. All right. So now we reran our regression with deviation coding. And this is the output. And again, I wanted to just walk through kind of the interpretation of these. So B sub 0 here is going to be the predicted value of Y when gender is at its grand mean. Remember, so by us centering this or deviation coding it, the intercept changes to the grand mean. It's grand mean, and age is at its mean. So this doesn't represent now the actual mean of that particular group. It's a little different.
Gender TRT in the model.
Oh, you're right. Good looking out. There you go. That's better. So B0 is the predicted value of Y when gender is at its grand mean. So now it's not any longer at its mean, right? For that particular female group. Now it's just at the grand mean and age is at its mean. B sub 1 is the slope of age when gender is at its grand mean. So this is the overall slope effect of age. You can interpret this as. B sub 2 is still going to be the offset or difference in the intercept. So nothing has changed here, right? So the difference is still 0.21. Just because that's what deviation coding affords us, right? So it gives us the difference. And then B sub 3 is still our interaction term. Right? So going from females to males for a 1 unit increase in age, right? So there's a 0.0135. And again, this is similar to what we did with the dummy coding here. So the B sub 3 is still going to be our interaction term, right? And we would see if that's significant or not, and it is. And then the gender dev, so since we deviation coded, it's still going to be the difference. What's different here is the intercept value and then the age slope, right? Because it's no longer at the female level, it's at the grand mean level. So slight differences in interpretation, but there's not too many differences. All right. So as Abby alluded to, the interaction is significant, right? So the p-value is less than 0.05, right? So what do? Do we just say that the interaction is significant and then just go on with our life? No, not quite. So generally speaking, when we have an interaction in our regression models, we typically don't explain the individual effects, right? So we don't really explain age and gender. So we don't explain those coefficients. I like to explain them, but generally speaking, we can ignore those individual effects and just focus on the interaction effect, right? And that's because there's dependency in our model, right? So those partial effects, those individual effects represent the unique relationship, right? But there's interaction there, right? So we don't want to interpret those. We want to interpret the interaction term. So what we do when we have an interaction is we have to follow up that interaction to determine where, the interaction is occurring. And so what we do is we perform what's called a simple slopes analysis. Sometimes this is called a spotlight analysis, and sometimes it's called like pick a point. But we're going to refer to it as simple slopes or spotlight analysis throughout. So what we're doing with the simple slopes analysis is basically looking at the association between age and gender at different values of Z. So what we're going to be looking at is the slope relationship, right? So between age and evaluation score at males and at females. So that's what we're going to be looking at. And we're going to be testing to see if that slope is not zero. So we're going to be computing a t-statistic and looking at a p-value for those slopes to see where there's a difference and where there's not a difference. So luckily, m-means will help us with this. So what I've done here is I've just refit the model. You don't have to refit the model, but I just basically assigned it to D. And we're going to use this function called m-trends. So we've been using m-means, and that will give us the marginal means or the means for the conditions, right? M-trends will give us the slopes. So when we're doing these kind of categorical by continuous or continuous by continuous, we're probably going to be using m-trends a lot. And essentially what we're going to be doing is we're going to be inputting our model that we fit. We're going to be telling it what our moderator variable is. So it's going to be gender treat. And then we're going to be telling it what our focal predictor is or what our IV is. And that's going to be age underscore C. So I've run this model 2 times and we get slightly different outputs. So let me explain why we get slightly different outputs. So when we run it the first time, I don't have this test function here. And if you don't put the test function, you don't get p-values and t-tests. And we need those p-values, right? So the first time we run it, we only get confidence intervals. So those are important. We want those. We want to report those. When we run it the second time with the test function, then we get a t-ratio and a p-value. So we have all the information that we need to report here. So in the first column here, we have gender treatment. So 0 and 1. Remember, 0 is female, 1 is male. We have our slope estimate here. So negative 0.02 and then negative 0.003. We have our standard error, our degrees of freedom, and then our confidence intervals and our t-ratio and p-value. What I want you to note is that this slope value here, this negative 0.02, is the same slope value that we got when we fit the regression model originally, right? Because of how we coded the model with females as 0. So if we go back to our model here, right, this is the slope for females. So we kind of get that for free, right? What we don't get is the male slope. So we could do some math here, right, and get the male slope, right? So we would take this estimate and then add that to the interaction estimate, and we would basically get this value here, this negative 0.003. So this is a slope for males. And what we see here is that for females, the slope is significant and negative, right, for females. When we look at the male slope, as Abby said, it's 0.00, right? So it's 0, and that is not statistically significant. So the confidence intervals for males include 0, and the p-value is greater than 0.05. For females, the confidence intervals does not include 0, and the p-value is less than 0.05. So we have a situation here where the slope is significant for females, but not for males. So again, this is where our interaction is coming from, right? But we need to be really, really careful here. So just because there is a significant slope in one condition, but not in the other, does not mean there's going to be an interaction, right? This happens a lot, too much, where individuals will say there's a significant effect in this condition, but not in this condition, there's an interaction. You must test the interaction effect, right? All the simple slopes is doing is just testing to see if that slope is not 0. It's not testing the difference. What's testing the difference is the interaction term here. And I'm going to highlight that here. So we're going to use the mtrends function here, and we're going to add an argument called pairwise. And that's essentially going to take the two slopes and subtract them from one another. So we get our simple slopes here, and then this is the test of the interaction. So this is the difference in slope. This is what the interaction is testing, just the difference in these two slopes. And the estimate is negative 0.0135, and then our p-value is 0.01. It's statistically significant. And this is the estimate that we get for our model. This is the interaction term. So essentially that's what it's looking at, right? The difference between those two slopes. That's what the interaction is testing. The simple slopes is just testing which one is 0, which one is not 0 in terms of the slope. And if you're interested kind of where this came from, I guess it was an issue before that, but this is a very, very, seminal paper. I suggest that you read it. This is something that when I'm reviewing papers, I will send to the paper writers. It is a very good paper. I love the title of it. The difference between significant and non-significant is not itself statistically significant. The paper itself is very short. It's about 5 pages, but again, it highlights this issue of saying that there's an interaction when you have a significant effect in one group but not the other. You need to test for the interaction. If the interaction is not significant, then you shouldn't be following up with these simple slopes analysis. A lot of people do this. You should not do it. So keep that in mind. I don't know if you've seen this in papers, but always check to make sure that if the interaction is something that's theoretically important to you, that you're testing it. All right, so we have a statistically significant interaction here. How should we visualize it? So we already kind of did this with the scatter plot, but again, we should highlight the non-parallel lines in our visualization. So a scatter plot with age on the x-axis and then scores on the y-axis with the differences in the slope would be a good visualization for visualizing this interaction effect. But what if we don't have an interaction? What if that interaction is not statistically significant? What do we do then? Well, what we can do is there's a little visualization technique. There's a function called GM parallel slopes that will just basically visualize your data with parallel slopes. So if you don't have an interaction in your model, this is one way you could visualize it. So it's not doing anything to your data or your analysis. Again, just for visual purposes, it's just making those lines parallel to one another. Because if you remember, if there's no interaction, the lines are parallel. It could be kind of misleading if you visualize the data and the lines kind of look not parallel. So this is one way that you can go about it. If there's no interaction, is just to visualize them as parallel.
Are you supposed to like compare this to your other scatter plot?
So I wouldn't compare it to the other scatter plot. So if you conduct the analysis and there's no interaction, I probably would just visualize something like this and say that there's parallel slopes. So when you don't have an interaction, then by default, essentially you have parallel slopes, right?
Yeah, I guess I'm confused about why we do this or what it's doing. It's just like forcing parallel slopes, right?
Yeah, it's just forcing parallel slopes.
Why would we want to do that?
Just for visualization purposes, just to say that they're parallel to one another. You don't have to do this. This is kind of a one visualization technique you could use. You could just present this, right? And then just say that there's no interaction. This is kind of an alternative to that where you just force them to be parallel just because they are parallel. Here it might be a little misleading if there's no interaction, right?
Yeah.
To say that
Misleading to like change it?
kinda, but I don't know. I kind of like this, especially if there's no interaction, just to say that they're parallel to one another. But you're right; you don't have to. This is kind of just an alternative technique. Again, it's not doing anything to the data; it's just visualizing them as parallel. But you're right; you don't have to. If you feel like you don't want to do this, you don't have to.
But it's not changing the data. How is it?
So basically, so it's not changing the analysis or anything. It's just basically forcing them just to be parallel to one another. That's basically all it's doing. Like we're not doing this. Like we're not manipulating the data itself, like in the analysis. We're just manipulating the visualization. Yeah, just the lines, just for visualization purposes. Nothing like in terms of like analysis or anything. But right, you don't have to. I'm not going to force you to do it. This is not standard. This is just an alternative way. So far what we've been doing is we've been fitting these interaction models, right? So we've been adding our individual effects and then adding the interaction. We could also adopt a model comparison approach to this, where we fit two separate models and then just compare them with ANOVA, so with the F-test. So we could do that. This is an alternative way, where first we're fitting a model with just our individual effects, and then we're fitting an interaction model and then just comparing them. So kind of similar to what we did with the polynomial regression stuff with the non-squared variable or the cube variable compared to a model with just linear term. We could do that here. We would get the same answer that we get from running just a regular regression model, right? So we do see that the interaction term is warranted, right? So this model adds the interaction term, whereas this particular model doesn't. And the F value is 5.98 and the P value is less than 0.05. So we can say that the inclusion of the interaction is warranted. So this is just an alternative way. Again, you could just add the interaction into your model and you can be done with it. Or you might want to do kind of a model comparison approach to see. Maybe you don't theoretically know if there's an interaction or not, or if you should include it, you could do this kind of model comparison approach with it. So to kind of reiterate, right? So if you have an interaction, you kind of make sure that you visualize the non-parallel lines. If there's no interaction, you might want to adopt kind of a parallel slopes visualization where it forces the slopes to be zero, but personal preference.
Should the slopes that you plot automatically drawn match exactly the model?
Yeah. Yep. This one, when you have to use that special function, again, it's in some like, some package that's not really widely known. So again, have you like, maybe don't do this, but again, just for visualization purposes, this is kind of what it would look like if you force them to be equal, which is what we're saying essentially when the interaction is not significant, that it's constant across the age variable or across another variable. So I have concluded a write-up or kind of a template of how you'd write up a categorical by continuous interaction. So you can use the report function, but again, don't use the report function verbatim. Use the report function to kind of get a general sense of your data and the statistical analysis. But we want to make sure that's human readable. So I created a template of what we just did. So all continuous predictors were mean centered and deviation coded. If you use treatment coding, you say that. So the results of the regression indicated that the model significantly predicted evaluation scores, accounting for 5% of the variance. So age was a significant negative predictor of scores. So with increases in age being associated with lower evals, gender was significant, with women having lower evals than men. And importantly, there was a significant interaction between age and gender. A simple slopes analysis indicated a significant slope for women. but not for men, a significant negative slope for women, but not for men. So while age does not seem to affect evaluation scores for men, evaluation scores tend to be poorer for older women in evaluations. So this is an example write-up to use for analyses that you're going to be doing in the future or for the lab on Wednesday. All right, so are there any questions about categorical by continuous interactions? Now we're going to get into continuous by continuous interactions. So kind of an open question and a contentious question is the relationship between violent video games and aggression. Are there any video game players here, PC players at all? So it's kind of like a huge debate going on now still. So the data set that we're going to use for this portion is going to look at that. So we're going to look at the relationship between how many hours you spend playing video games and aggression scores. But we're going to look at a moderator. We're going to look at callous unemotional traits. So people high in callous unemotional traits are more likely to engage in kind of antisocial behavior and criminal behavior. So we're going to look at the relationship between hours played and aggression and whether callous unemotional traits moderates that relationship, right? So there's not a simple one-to-one relationship between how many hours you spend playing video games and aggression scores. So that's what we're going to look at. So let's go ahead and run that code. Awesome. So to actually visualize a continuous by continuous interaction, it's kind of difficult to visualize it. So remember when I was talking about kind of the wrinkly blankets? So that's kind of what we would see if there's an interaction between continuous variables. So this kind of doesn't do it justice, but imagine, and can't even see that on the projector, but if there was no interaction, this regression plane that we're fitting right would be flat. We see that it's kind of tilted. So if it's tilted, in different directions, then that means that there's some type of interaction. So imagine a wrinkly blanket. That would be indicative of some type of interaction. So it's very hard to kind of visualize multiple variables interacting with one another. So in our data set, we have two continuous variables now. So we should center those variables. Again, reduces multicollinearity and aids in interpretation, especially if you don't have 0 in your data set. So let's go ahead and mean center our data. So in our data set, we should have video game C and then the seance C. These are all centered. In hindsight, that's probably a horrible name for this variable, but whatever. All right, so before we start interpreting our regression model, I wanted to provide kind of a general interpretation of a continuous by continuous interaction. So in this model, right, we have X, which is a continuous predictor, and our moderator variable Z, which is uncallous emotions, is also a continuous predictor. So how do we interpret those coefficients? So here, B sub 0 is the intercept or the predicted outcome when both X and Z are at its mean or when they're 0. Simple enough. B sub 1 is the slope of X. So for a 1 unit change in X, the predicted change in Y when Z is equal to 0 or at its mean. B sub 2 is the slope of Z. So for a 1 unit change in Z, the predicted change in Y at X equals 0 or at its mean. And B3 is going to be our interaction term between X and Z. So it's the change in slope of X for a 1 unit change or 1 unit increase in Z or vice versa. All right, so let's go ahead and fit our model and let's interpret some coefficients. So we fit the model, right? So we have our mean centered variables in our model, and then this asterisk right here will essentially give us the interaction term. So what does B sub 0 represent here? So 39.97.
Is it aggression score?
As our DB?
Yeah.
Yeah, aggression scores are DB, yep.
Okay, yeah, it's the aggression when the video game's hours is at its mean and callous emotional.
Yeah, yep,
Is at its mean.
yep, correct, yep. So it's the expected value. I could spell. Value of aggression when hours and traits are at its mean. If you didn't mean center the data, it would just be when those particular variables are at 0, right? All right, so what about B sub 1? So this is hours played video games. So this would be interpreted similarly what we did when we looked at multiple regression coefficients, right? When continuous variables.
It's the slope of hours played when so like for when the unemotional traits is at its mean.
Yep. Correct. Yep. So it's just the slope of hours played when traits are at its mean, right? So for a 1 unit increase in hours played, there is a 0.17 increase in aggression scores. So what about B sub 2 here, which is the trait score? So it's basically the opposite of what Aditi said. So this is the slope of traits when hours is at its mean. Right? So for a 1 unit increase in traits, there is a 0.76 increase in aggression scores. What about our B sub 3 coefficient?
Interaction between
Mm-hmm.
traits and output.
Yep. So this is our interaction term, right? Between hours played and traits. So this is going to be the difference in slope of hours, or excuse me, of traits for a 1 unit increase in hours played, right? So as hours played increase, or so as we increase in uncallous traits, how does the slope change between video games and aggression scores? That's our interaction term here. And is this interaction significant? So do we have a significant interaction here in our model? Yes, yes we do. So what do we do with this information? So when we looked at a categorical by continuous interaction, right, we were able to look at different levels of the moderator, right? We had 2 levels, males and females. Well, now we have a continuous moderator. So what the heck do we do, right? So we're going to have to do something similar to kind of a simple slopes analysis or spotlight analysis here. So what's common when we're dealing with a continuous moderator is basically we're going to kind of partition our continuous variable into separate groups. So what we usually do is we create what's called a low group, an average group, and a high group. So low groups are people who are 1 standard deviation below the mean. Average groups are people at the mean, and then high groups are people 1 standard deviation above the mean. So we're doing something very similar to our spotlight simple slopes analysis with a categorical predictor, right? So we're essentially creating groups instead of looking at this as kind of one continuous range. So how do we create these groups? So the low group we create by just subtracting 1 standard deviation, right? So I have that highlighted here, so I labeled that as B. For the high group, what we're going to do is just take the mean of our moderator and then add 1 standard deviation to it. And then for the moderated value at the mean, we're just going to take the mean. So those are our 3 points that we're going to look at. And that's how we're slicing up this continuous moderator. So we can use our mtrends function from mmeans to do this, but we're actually going to have to first create a list with our values that we've selected. So that's what I've done here. So I've created a list with basically the value below the mean, at the mean, and then above the mean. And I just rounded those values, right? So we get nice whole numbers. This is just running the LM model again. If you've already saved this as D or whatever you saved it as, you don't need to do this. But what we're going to do is we're going to input this model into mtrends. We're going to state what our moderator variable is, and then what our focal predictor or independent variable is. So this is video games. And then we need this at function. And this at function is going to be the variable that created my list. And my list has 3 values in it. The value is 1 standard deviation below the mean, at the mean, and above the mean. Those are the 3 values that we're going to look at. And what we want to also do here is we want to use our test function so we can get our t value and our p value, but I've also adjusted the p values for multiple comparisons. So as we do more and more simple slopes analyses, right, we're doing multiple tests. So that's going to inflate our p values here. So it's always a good idea to adjust those p values. I did not run this. So we have to run this first and then run this. Awesome. So again, this is very similar to the output that we got for the simple slopes analysis for our categorical by continuous regression model. But now we have 1 standard deviation below the mean, at the mean, and above the mean. And then we also have our slope estimates for each one, and then whether they're significant or not. Remember, if you want the confidence intervals, you'd have to run a separate model without this test function here. So that's kind of cut off. So looking at the t or the p values, what we can see here is that there's 2 significant slopes. We see at average levels, the association between hours played and aggression is 0.17. And then we also see at 1 standard deviation above the mean that there's a significant slope of 0.42. So we see here with our data that the effect between hours and aggression scores is significant at average levels of callousness and also at high levels of callousness. So what does this look like? Well, so there's 2 different packages that we can use to visualize our data, and we could use these also for our categorical by continuous if we wanted to. But I think that this, in 1 line of code provides pretty nice looking visualizations of this, and it does it automatically. So what we've done here is we've used the interact plot function from interactions. We've put in our model, which we labeled as D, our predictor variable, which is video games, hours played, and then our moderator, which is this mod X, is our callous traits. And then I said plot points and then also provide intervals. So this is the confidence intervals around those lines. And this is kind of the visualization, and it's really, really hard to see. I wonder if I turn off the lights here. Nope. Still not good. Oh well. So essentially we have 3 lines here, right? With our categorical predictor, we had 2 lines. We have 3 lines here. The middle line represents the mean. We have 1 standard deviation above and then 1 standard deviation below, right? So 1 standard deviation below was not a significant slope, right? The significant slopes were for mean and 1 standard deviation above. So that's what we would interpret as arising from our interaction. We could also use ggpredict, which we've used in the past. Again, 1 line of code, and it creates pretty nice looking figures. Maybe this one is a little bit easier to see. So obviously I should have modified these, but I didn't. But again, we can see the same figure. And now we have these numbers here. Those just represent 1 standard deviation above the mean and below the mean, and then at the mean. Those are what those numbers represent here. So the simple slopes or the spotlight analysis, we're picking points, right? So we're basically cutting up our continuous variable, right? And picking 3 points. A more powerful approach, and one that I think that is becoming more used in the literature, is what's called the Johnson-Neiman procedure. So instead of just picking points of our moderator to look at, what we do is we basically look at the whole range of the moderator. right? So instead of a spotlight analysis, this is kind of like a floodlight analysis where we have kind of a light over all of the values in our moderator value or in our moderator variable. And essentially what we're doing here is we're just looking at the simple slopes, but at each level of the moderator. So instead of having something like, 3 lines, right, we're going to have whatever, 55 lines where we're testing the slope at each point of the moderator. That's what this Johnson-Neiman procedure does. And what we can do is we could define a region of significance, non-significance across the slope. So let's see what that looks like. So what we're going to do, so we could probably do this with m-means, but it would require a lot more lines of code. And ggpredict does this fairly easy. So ggpredict is from ggfx. And in a couple lines of code, we can have nice looking figures and also hypothesis tests. So we're going to use our ggpredict function here, and we're going to input our model. And then we're going to input our focal predictor, which is hours played, and then our moderator variable. But you'll notice here that I have this all in brackets. This tells us that we want to look at each value of the moderator. So when we put this in here, it'll output each value of the moderator. What we can do with this is we can feed it into this hypothesis test function from ggfx. And then we input our object, our PR object. And then we want to adjust our p-values for this, right? Because we're doing multiple comparisons. And basically we get a table that looks very much like the M-trends table, right? So we have each value of our moderator and then the slope and then the confidence intervals for that slope and then our p-values. So essentially what we're going to do is we're going to take this table and we're going to produce a visualization of that table. And to do that, there's a function called Johnson-Neiman that is in ggfx. And it's going to produce well, it doesn't look nice here, but it looks nice on the slides. Basically, you're going to produce a visualization of this, of these hypotheses tests. And what we want to notice here is that there's a region, a dotted line, two dotted vertical lines that kind of segment the significant from the non-significant. So the blue in the figure is the significant, and then the red is the non-significant. And what we see here is that for higher levels of the callus traits, we see a significant effect. So these right now, I have an issue submitted to the ggfx person. So these don't correct for multiple comparisons. So if we look at our actual table here, this does correct for multiple comparisons, and the values that it's saying are significant here are not significant here. So this is going to be corrected. So if you're ever going to use it, you can correct for multiple comparisons and the plot should reflect that. But what we see here essentially is at higher levels, we have more significant effects. So higher levels of callus traits, the relationship between hours played and aggression are stronger here. And what I like about this Johnson-Neiman is that it actually produces some verbiage for you, so you can actually interpret the plot. Sometimes they're kind of difficult to interpret. So it says the association between video games played, so hours played, and aggression is negative for values of traits lower than negative 16.20. So this should not be significant. So we can ignore that. So all we get are significant effects for all we're getting are significant effects for higher values of callus traits, right? So higher than negative 1.30. So as callus traits increases or gets higher, we have a stronger relationship, a stronger positive relationship for hours played and aggression scores. So what I have here is a sample write-up of our continuous by continuous interaction regression model. So what I say is all continuous predictors were mean-centered. The results of the regression indicated that the model predicted violent behavior scores, accounting for 37% of the variance. Hours was a significant positive predictor of violence, with increases in hours played associated with higher levels of violence. Callus traits was a positive predictor of violence, with increases in callus traits being associated with higher levels of violence. Importantly, there was a significant interaction between hours played and callus traits. So following up with a simple slope spotlight analysis, if that's what we chose to do, showed the effect was significant at average levels of callus traits and high levels of callus traits, but not at low levels of callus traits. Thus, hours playing video games and violent scores is moderated by callous traits. Specifically, the relationship between hours playing video games and violent scores is strongest for those with high callous traits, which kind of makes sense. So overall, just playing lots of video games doesn't make you more aggressive. It seems like these callous traits moderate that relationship. I also have a sample write-up if we're going to use the Johnson-Neiman technique. So since the moderator was continuous, we looked for turning points. So where in the value of the moderator, the effect turns from non-significant to significant. So I said the Johnson-Neiman technique showed that the association between hours played and regression is positive for higher values than negative 1.30. So inside the interval of negative 16 to negative 1.3, there was no clear associations or the effect was non-significant. Overall, there seems to be a detrimental effect between hours played and aggression at high levels of callous traits. So this is kind of just a sample write-up of the Johnson-Neiman procedure if you're going to use that for your analysis. So one package I wanted to highlight by my good friend Erin Buchanan. She created this package called the Mimo boot R package, which is fun to say. And the reason why I like this particular package is because it does pretty much all the moderation analysis for you in like one function. So we can't download this from CRAN, so instead you have to download it from GitHub, but we can load the library in. And then there's a function called moderation1. And basically we can state what our Y variable is, which is aggression, what our X variable is, which is our focal predictor, and then what our moderator variable is. And then we can run this function. You don't need to center the variables because it does it for you already. So you could just throw your variables into this function and it will output a whole bunch of good things. So let's go ahead and do that real quick. So when we run this in the console, there's going to be a whole bunch of objects that are within that object itself. One thing is data screening. So this will actually do the data screening for you, and you can just look at the actual output of that. So we can look at the linearity of our model. So what do you guys think? It looks pretty good, right? We can look at normality. It'll produce a nice little histogram. Look at homogeneity, produces homogeneity plot. I mean, it's not as nice as the Easy Stats performance package, but I think it, I like that it just has everything within that one particular object. It also gives you regression results. So it gives you the regression results for one standard deviation above the mean, below the mean, and at the mean. So to get those, we just fit the model at one standard deviation above the mean, below the mean, and at the mean. So basically you have regression output here, right? So X here is video games, and this is the slope that we're interested in. These are the same slopes that we'd get when we do M trends, or if we fit the model. So we get that stuff. So at low, high, so all that good stuff. It gives you an interpretation, which is also, nice. So it gives like a little output of each level. So at low levels, so one standard deviation below the mean, at the mean, and above the mean. So we get that. And we also get a graph. So it'll produce a graph for you. It's not very colorful. It's just black and white. But again, I like that you can just get all of this from one call. Or not. There we go. So you get something like that automatically. So that's kind of nice. And you should be able to do this too with a categorical predictor, or a categorical moderator as well. So this is just highlighting it with a continuous by continuous. So if you wanted to use that. And this slide just has all the things that I just went through to look at all the different components of the object. So with the remaining time that we have here, I wanted to talk a little bit about power as it relates to these type of models. So far we've been using this web power regression calculator. We can do that with our interaction models as well, right? We're just adding another predictor to our model. So we can use this regression calculator if we want to do something quick and dirty to get an estimate of power, right? So we would just have to change our P1, which is the number of parameters in our model. So we just have 3, right? Because we have the interaction value. F2, I just made that number up. I don't know what F2 is in this. So basically you remember you take the R squared and then you convert that into F squared. And then you can calculate your power for the model itself. So pretty easy. A package that I've just come across recently called Interaction Power does simulation methods to look at the power of interaction models. And I haven't had a lot of time to play around with this, but I think it's a really cool package. I have reference to the paper here. So if this is something that you're interested in, if you're doing these, continuous by continuous interaction models or 3-way models, I think that this will actually be extremely helpful. And what I like about it is that it's fairly simple and straightforward, which is always good, right? All that it requires are 4 correlations that you can compute easily from your data. It requires the correlation between X and Y, so your focal predictor in Y, the moderator in Y, and then the interaction in Y, and then the interaction between X and Z. Right, so we know that correlations are kind of effect size measures, so we can actually use this and input it into our model. What I really like is that there's a Shiny app for this package that makes things really simple to run and use. So you don't have to really write any code if you don't want to. So let's hopefully this opens up. That is horrible. You guys can't probably read that. Let me just zoom in a little bit. But essentially, damn it. But yeah, so it has some instructions about each of the different arguments here, right? So unless you input the number of simulations, the alpha level, number of clusters you don't need to worry about, and also the seed, put in whatever seed you'd like. What you can do is you could do like a power curve type of thing here, where you can input separated by commas, the sample size. So we can input our correlations from our actual data set. I'm just gonna input whatever here, right? So let's say that we looked at our data and calculated all of our correlations. We can put that in here. Reliabilities, you don't really need to worry about. What's cool here is you can actually set the variable type. So here we're just using continuous by continuous, but you can change the Y variable to be binary, right? If you're looking at logistic regressions. Or you can change your X or your moderator variable to be binary here. So we can do categorical by continuous interactions. We can do continuous by continuous interactions. There's actually an extension to do 3-way interactions. So for interacting 3 variables. So I think that this is very simple to use and easy to use and also useful. We can change our target power here. So we can add our parameters here and then say we want to look at power of 90. I'm going to change the number of simulations to like 200. So it runs. And then we just run it. So it'll produce a power curve that indicates the number of the samples that we need to get 90% power. So here what this says is that to get in about 90% power, we need about 600 participants in our data set. And then it produces this nice little power curve graph that we could just download and input into our paper. You have papers coming up. I don't know if anyone's doing interaction models. I think Aditi, you're doing interaction stuff. So this might be useful for that part of the paper. But we get a nice little power curve plot here, and I think it's simple to use. But if this is something that you're interested in, I would definitely recommend reading the paper. The paper is very short. It's a tutorial paper, which are my favorite type of paper. But I think it's useful. All right, so that is all that I have for at least interactions. So continuous by categorical and continuous by continuous. Next time, we're going to look at categorical by categorical interactions. And if something is confusing, I definitely suggest reading the textbook chapters on Canvas on interactions. I think they're really good as kind of a general introduction to interaction. So if you haven't done that, I would definitely recommend reading that to supplement the content from today. So does anyone have any questions about interactions, life in general? I always ignore the Zoom. I don't know if Renata has anything to say. Probably not. But if you guys don't have any questions, you're free to go.
I don't know why this happens, but whenever I'm in PDF export mode, some of the like symbols.
Yeah, I
get
noticed that
deleted.
too. I don't know
Yours
why.
was fine. I was looking over at Kennedy's and hers was fine, so I was like, I don't know.
Oh, so I'm not using PDF mode. I'm just using HTML mode. Yeah, no, I noticed that too. Like some of the equations and stuff are like off the page or like they don't appear,
Yeah.
which is very odd.
Oh, okay. I don't know why. I was
So I think that's just PDF mode.
Okay, and to do the HTML mode, is it still here? Or?
Yep. So HTML mode is just like if you just go to the website and then click on it. So go schedule, and then this is just HTML mode.
Oh.
And you can just
okay.
like go through it.
Got
But
it.
if you write any notes on it, it doesn't save.
Okay, yeah.
So like
that's
if
why I
you
had
if you write your
PDF.
notes on HTML and then you try to like put it into a PDF, like all of the notes will be
Yeah.
gone.
Okay.
So I would probably just suggest opening up the Cordo document and then just typing
Doing it
notes
that
in that
way.
way.
Yeah.
Here,
Okay.
and then I'm going to go on a run or something to tire myself out.
Oh, Snoop.
No, I just never wear that.
I love it.
I always wear my black ones.
The season for our platform docs.
Exactly.
It's always the season for platform
I
docs. What are you
know,
talking
yes,
about?
actually. I do.
Bye. See you on Wednesday.
Sounds good.
What is our final project? Is it like our whatever our scheduled final?
Yeah, for finals.
Okay.
And it's pretty flexible.
Okay.
Um, but yeah, no, you have like several weeks to do it. Like honestly, it's like a very short paper, so it shouldn't take too long.
Okay,
Yeah.
cool.
Like I don't want to read anything like longer than 10 pages.
Okay, perfect,
I want straight to the point. I want like a paragraph or two of introduction, a paragraph or two of results, and then conclusions.
Okay.
Just to get you guys started.
See you Wednesday.
See you on Wednesday.